Jai Shri Gurudev. Dear students, welcome to session 5 of module 2. In today's session, we'll discuss about an important formula which is used to solve the given signal flow graph termed as Mason's gain formula. In the previous session, we have discussed about block diagram representation, signal flow graph representation and terminologies that is used in the signal flow graph representation, and you have learned about nodes, branches, forward paths and so on in the last session. In today's session, we will see how the Mason's gain formula is used to evaluate the signal flow graphs. This is the outline of my session today. So today we'll discuss about Mason's gain formula and then we'll take a few examples on the same. So Mason's gain formula or Mason's gain rule was introduced by Mason in 1953. So generally the block diagram reduction technique requires successive applications of fundamental relationship in order to arrive at the system transfer function. So that means we need to apply so many reduction rules to arrive at a required transfer function for a block diagram. So for few block diagrams, this reduction rules holds good, but when we get a complex block diagram, it's become too tedious for anybody to apply the reduction rule to obtain the transfer function for the given block diagrams. For that purpose, Mason's uh, gain formula was introduced for signal flow graphs. So what it does is, this rule, it is used for reducing the signal flow graph to a single transfer function, and it requires the application of only one formula. And this formula was derived by the person named as S.J. Mason, where he related the signal flow graph to the simultaneous equations that can be written from the graph. The transfer function of a control system usually, as you know, it is represented by C of S by R of S, where C of S is considered to be the output of the system and R of S is considered to be the input to the system. So the ratio of Laplace transform of output to the input is nothing but the transfer function. This we have discussed in the beginning only. So in the signal flow graph representation, a transfer function is represented as C of S by R of S is equal to, so this is the formula, Mason's gain formula, which is used to find out the transfer function from the signal flow graph. So which is given as C of S by R of S is equal to summation I ranging from 1 to n pi delta I by delta. So here n is nothing but the number of forward paths and pi is nothing but the ith forward path gain, and delta is the determinant of the system and delta I is the determinant of the ith forward path. So forward path, as we have discussed in the previous session, it is nothing but the number of ways by which you can reach from input to output without repetition of the node and without changing the direction. And delta is called as the signal flow graph determinant or characteristic function. Since delta is equal to 0 is the characteristic equation for the system, and this delta usually it is represented as 1 plus summation of loops minus summation of two non-touching loops. So called as non-touching loops followed by plus summation of three non-touching loops. So same thing, non-touching loops. So this is the formula that is used to find out the determinant of a signal flow graph using Mason's gain formula. This is the systematic procedure that is used to solve the given signal flow graph. The first step is you need to calculate the forward path gain Pi for each forward path I. And then the second step is calculate the loop transfer function, that is you need to determine the number of loops and their gains, and then Once all the loops are evaluated, the third step is you need to find or consider the non-touching loops 2 at a time. That means you need to find out 2 non-touching loops if it is available. Then similarly you need to find out 3 non-touching loops if it is available, and similarly if you can have 4 non-touching loop, 5 non-touching loop, and so on, etc. So you need to determine all these non-touching loops. And the next step is you need to calculate the delta using the values that you have got in the second, third, fourth and fifth step. So once the delta value is evaluated, you need to calculate the determinant value for the ith path as a function of delta by considering the non-touching forward path I. So in the delta value we are going to eliminate the loops which doesn't touch the forward path. So this is the step or the systematic approach that is used to find the transfer function for a given signal flow graph. So please do follow the same steps. So first calculate the forward paths, then calculate the loop gains, then non-touching loops you need to evaluate. So using all these loop gains we need to calculate the determinant delta, and from the determinant delta we need to calculate the ith determinant which doesn't touch the forward path. So this is the general procedure which is followed to evaluate the transfer function for a signal flow graph. Now let's take a few examples and we'll see how this works out. So this is the question or an example which we are taking. So the question is, apply the Mason's rule to calculate the transfer function for the system represented by the signal flow graph which is given in the figure. So a signal flow graph is given to us. Our task is to apply Mason's rule and find the transfer function for the signal flow graph. So the first step is we need to evaluate the forward paths as it is shown in the slide. Forward path is nothing but the number of ways by which we can reach from input R to output C. So without changing the direction, you need to start from R, you should reach end. Okay, so we will start like this. So from this node to this node we are going in a straight manner and we are reaching the output. This is one forward path. So we need to multiply the gains that come across this forward path. As you can see, directly we are moving from R to C. The gains that is coming in this particular path is G1, G4 and G2. So just multiply the gains which comes in that particular forward path. So I am representing the first forward path as P1, and the total gain in this particular path is nothing but the multiplication of the individual gains that come in the particular forward path. So the gain is taken as G1, G2 and G4. So this is one forward path what we have. So another forward path is, see, I'm starting from R. So I cannot go like this. I need to go straight. So here you have one forward direction like this. I am writing it in green color, please to observe, and then I am reaching my C. This is one forward path. So this is represented as P2, and the gain that comes in this particular path is, we have G1, G4 which is coming in the path. Along with that we have G3, then 1, 1. So the forward path gain for the second forward path P2 is G1, G3 and G4. So we will search, do I have any other forward path? Let's see. So if I take like this yellow color, please to observe this. I'm going like this, but I cannot go like this. It's wrong because you have a change in the direction. It's a feedback. I can't go like this. So I'll try like this. So can I go like this? No, not possible, because this is also wrong, because you have H1 which is coming in the reverse direction. So here I have only two forward paths. Now after finding the forward paths, the next step is you need to find the number of loops. Loops is nothing but what? You will start from one node, you will end at the same node. So this is the general Mason's gain formula which I am using it. C by R is equal to P1 delta 1 plus P2 delta 2 by delta, because I have two forward paths. So you need to have two forward determinants, delta 1 and delta 2, and a general determinant delta you need to find out. Okay. Now we will find out the number of loops, feedback loops. Let's see. So here we are trying to find the number of loops. Let's see. So as you can see, you will be starting from one node and you have to reach the same node. So let's take this. So this becomes one loop, yellow color 1. So just multiply the loop gains here. That becomes your L1. So this is my L1 which I have highlighted in yellow color. So the gain here is G1, G4, H1. So this is my first loop. And similarly, I need to search for the remaining loops. So I'm writing it here in red color. I'm starting from the same node. I'm going like this. So you have one feedback here. You're coming back like this and you will be reaching the node. So this is one more loop which I'm naming it as L2. So L2 is this one. So what is the gain that is coming across here? G1, G4, G2 minus H2. Sign also you are supposed to consider. So the loop gain for L2 is minus G1, G2, G4, H2. Now L3, I'll show L3 loop. So same node, I'm starting like this. I'll go like this. I'll bifurcate G2 and I'll use G3. So this is my another loop which I'm writing it in green color. So it is G1, G4, G3 into 1 minus H2. So the loop gain for your loop L3 is G1, G2, sorry, G1, G3, G4, H2. So there are 3 feedback loops which I have named it as L1, L2 and L3. Now after this you need to search for number of non-touching loops. So we will take 2 loops at a time. So let's see whether L1 touches L2. The easy way to identify this is just see whether any of the gain whatever I have here in L1 is it repeated in L2. See, you have G1, here also you have G1, you have G4, here also you have G4. That means that these 2 loops they touch each other. So I don't have a non-touching loop between these two, L1 and L2. Similarly, compare L1 with L3. Now I am comparing these two. Okay. So here you have G1, here also you have G1, you have G4 here, here also you have G4. So these two also touch each other. Now the next thing is you need to compare L2 with L3. So if I compare L2 with L3, again here we have G1 and G4 which is coming here. So all the loops touch each other. So there are no non-touching loops. So no non-touching loops. So you can stop at this point itself. So you do not have to check for 3 non-touching loop because you don't have 2 non-touching loop itself. So just you have to write there is non-touching loop is nil. So there are no non-touching loops, it is nil. Now once you evaluate this, the next step is you need to find out your delta value and then your delta 1 and delta 2 values. So here we are trying to find the delta value which is nothing but equal to, here since I don't have any non-touching loops, I am just taking my delta as equal to 1 minus sum of all individual loops. Okay, so it is equal to 1 minus L1 plus L2 plus L3. So whatever loop gains you have for L1 and L2, L3 should be summated and it should be taken as your delta. So this is what is the delta value we are going to get. Delta is nothing but equal to 1 minus G1 G4 H1 minus G1 G2 G4 H2 minus G1 G3 G4 H2. I have included all the loop gains here. So that becomes your delta value. Now the next step is you need to find out your delta 1 and delta 2. Now how to find out delta 1 is, so eliminate the forward path 1. So that means in the forward, in the delta value, you need to eliminate the loops which touches the forward path. So we have L1, L2 and L3. So if you can observe here, this is our L1, this is our L2 and one more is this is our L3. So all these loops, they touch this forward path. So delta P1 is this route. So all these loops are appearing in this forward path. So you need to eliminate this. This will not come into picture for delta 1. So delta 1 is just taken as equal to 1. Now similarly, you need to evaluate your delta 2 also. So delta 2 is nothing but equal to eliminate the forward path 2. Okay, so you need to eliminate all the loops which will come in your second forward path. So our second forward path is this. So if we can observe here, this is your L2, this is your L1, and L3 is nothing but this. This also will come here. So all these loops, they touch the second forward path P2 also. So that means here also I'll be eliminating this sum of all the individual loop gains. So delta 2 is also taken as equal to 1 in this case. So this is how you need to find out your delta 1 and delta 2 values. For example, if I consider any one of the forward path, if one of the loop, if it doesn't appear in this particular path, then you have to consider that. Okay. So this is how your delta 1 and delta 2 values are evaluated for the signal flow graph. After this, the last step is you need to combine all these values using the Mason's gain formula. So this is the result what I've got for the given signal flow graph. So C of S by R of S is equal to P1 delta 1 plus P2 delta 2 divided by delta. So delta 1 and delta 2 is equal to 1. So I'll be getting only P1 plus P2 in my numerator. So it is G1, G2, G4 plus G1, G3, G4. So divided by 1 minus G1, G4, H1 plus G1, G2, G4H2 plus G1, G3, G4H2. So if you want, you can stop at this point also, or further if you want to simplify, you can take the common terms in between these two values. So here G1, G4 is common in both the terms, in these two terms. So I've taken that as common. So it is taken as G1, G4 into G2 plus G3. So this is the final transfer function what we are going to get for the given signal flow graph. The same thing if you want to solve in the block diagram representation, almost you need to apply around 6 to 8 rules to reduce a block diagram. So signal flow graph could be easily solved using the Mason's gain formula. That is the main advantage. I hope the concept is clear. So if you understand one problem thoroughly, you can solve any other problems on signal flow graphs. So this is the procedure what we need to follow. I am repeating it again. First find the number of forward paths, then find the number of loops. Now after finding the number of loops, then you need to evaluate the 2 non-touching loops if you have. Then again if you have 2 non-touching loops, then you need to determine 3 non-touching loops and 4 non-touching loops and so on. So once this is evaluated, the next step is you need to find out your determinant value, delta value, by using the formula, and then delta 1 and delta 2 values. So finally combine them everything using the rule to get the final transfer function for the system. So let's take few more examples on this, then you thoroughly understand. So this is one of the important problem which is most oftenly asked in the examination. So here let's see how many forward paths are there. So first is, this is my R, this is my Y. So R is my input, Y is my output. We need to calculate the transfer function for this particular problem using the signal flow graph representation and Mason's gain formula. So one way is highlighted in red color. Observe here, it is you are starting from R, then you are reaching your Y. This is one direction. Another direction is like this. It's highlighted in blue, so you are going like this. So P1 is taken as G1, G2, G3, G4. That is multiplication of all the gain G1, G2, G3 and G4. Now similarly, the second forward path gain is G5, G6, G7 and G8. So do you have any other forward paths in this? So I can start like this. I can go, it gets repeated. So we have 2 forward paths. Now coming to the number of loops, as you can see here, this becomes your one loop, this is your second loop, and this is your third loop. You're starting like this and you're going here, and this is your fourth loop, which are represented as L1, L2, L3 and L4. So L1 gain is G2 into H2, L2 gain is G3 into H3, L3 gain is G6 into H6 and L4 gain is G7 into H7. Now coming to the non-touching loops. Okay, so when you are comparing it, so compare L with all the 3 loops. Just check whether any gain is repeated. So if I compare these two, or any gain or any node, if it is getting repeated, then you should not consider them as non-touching loops. So L1, L2, see L1 is this, L1 is this, so P1, this node is common, so I cannot, this node is common between these two, so I cannot consider, they touch each other, so leave this. Now compare L1 with L3. So L1 does not touch L3. So this is on the upper side and this is on the lower side, and there is no gain which is getting repeated. So L1, L3 is one non-touching loop. Similarly, compare L1 with L4. So these two also, that does not touch each other. So I got two non-touching loops. So you need to multiply the gain of these loops which doesn't touch each other. Then compare L2 with L3. L2 doesn't touch L3, and similarly L2 doesn't touch L4. So I here again I got two non-touching loops. So totally four non-touching loops till now. Now compare L3 with L4. So here L3 and L4 touch each other because there is a common node between these two. So totally I have got four non-touching loops, that is L1, L3, L1, L4, L2, L3, L2, L4. So these are the non-touching loops that I have. That is what I told you, L1, L3, L1, L4, L2, L4 and L2, L3. So these are the two non-touching loops that I have. Now coming to three non-touching loops. So if I try to find the three non-touching loops, when you are finding the three non-touching loops, how you do the comparison is, you have to take three loops at a time. Now take L1, L2, L3. So L1, L2 touch each other, so I cannot take this. Similarly, now take L1, L3, L4. So L1 doesn't touch L3 and L4, so I got one non-touching loop. So here L1, L3, L4, but here L3 and L4 touch each other, so I cannot take. Similarly, now compare L2, L3, L4, they also, one of the loops L3 and L4, they touch each other, so there are no three non-touching loops. So three non-touching loops are nil. So that is what is shown here, it is none. Now calculate the delta value using the loop gain values what we have got. So delta is taken as 1 minus L1 plus L2 plus L3 plus L4 plus L1 L3 plus L1 L4 plus L2 L3 plus L2 L4. So just replace all the gains here, you will get your delta value, determinant value. Now after this, the last step is you need to find out your forward paths. Okay, so here if I take my first forward path, okay, so in that case your delta 1 is taken as 1 minus L3 L4, because L3 and L4, this is my first forward path, so these two, they does not touch this particular forward path, so you have to take L3 and L4. So it is 1 minus L3 L4. In the previous problem, if you can see, all the loops were touching the forward path, but here these two L3 and L4 loops, they does not touch the forward path P1. So this is my forward path P1. So they are not touching it. So delta 1 is taken as 1 minus L3 plus L4. So it is nothing but 1 minus G6H6 plus G7H7. And similarly, delta 2, when you are finding it out, you have to, this is my second forward path what I have. So these two loops, that is L1 and L2, does not touch this forward path. So my delta 2 is taken as 1 minus L1 plus L2. And if you replace the gain value of L1 plus L2, it is taken as 1 minus G2H2 plus G3H3. So we have evaluated all the values. Now the last step is you have to replace all the values to determine your transfer function. So y was my output and r of s is my input. So your formula is P1 delta 1 plus P2 delta 2 divided by delta. So you have evaluated all the values. So P1 is G1, G2, G3, G4 into 1 minus G6, H6 plus G7, H7 plus G2, G6, G7, G8 into 1 minus G2, H2 plus G3, H3 divided by the delta value. So this is the final transfer function what I am going to get for the signal flow graph. Now similarly, one more example is given. So same concept you need to apply for this example also. So first step is you have to evaluate the forward paths and the loop gain. So here, how many forward paths I have? So I have one forward path from here to here. Okay, then the number of loops is equal to L1, L2, L3, L4, and non-touching loops, if you can observe here, so L1, L2 does not touch each other, L2, L3 does not touch each other, but L4 touches with all the loops. Okay, so same thing is applied here also. So you'll get a delta value like this. So summation of all the loop gains followed by you have two non-touching loops, and this is the delta 1 value what we have. So the loop that doesn't touch the forward path is only this loop, so that is taken. So delta 1 is 1 minus G7 H of S into H4 of S. So this is our next example, so wherein you have to find out the number of forward paths in the similar way. So we will find out the forward paths first. So it is highlighted in the yellow color here. So from x1 to x8 we are reaching like this. So the gain that you will come across here is getting multiplied, which is represented as P1. Similarly, you have P2. So directly from here you are going like this, which is highlighted in blue color, red color. I'm showing it in red color. Then P3, you will start like this, you will go like this. Okay, so that is one forward path, P3. Now coming to the non-touching loops. So here, log number of non-touching loops you will get L1, L3, L1, L4, L1, L5, L1, L6, L1, L8, L2, L4, L2, L5, L2, L6, L2, L8, L3, L5, L3, L6, L4, L6, L4, L7, L5, L7, L7 and L8. So these are the two non-touching loops we have. And similarly, you have three non-touching loops also. So where you will be taking the product. And finally, your C of S by R of S is taken as P1 delta 1 plus P2 delta 2 plus P3 delta 3 divided by delta. Okay, this is about the signal flow graph and Mason's gain formula. So using the Mason's gain formula or the rule, we can directly simplify the given complicated signal flow graph and we can evaluate the transfer function. So in today's session, we have learned about Mason's gain formula and we have taken few examples on the same. So try to solve as many problems as possible. Just try to remember the steps that you need to adopt to solve the signal flow graph. So these are the references books from which I have taken the problems. And you can refer these books for extra problems also and try to solve them. Thank you all. Have a nice day. Jai Shri Gurudev.